Okay, for people who are joining this live stream, we are continuing our discussion of the difficult but very important topic of multicomputation. And this is about computation where there is not one thread of evaluation, one thread of time, and there are many different applications for this. And we are trying to understand how to make a general framework for dealing with these kinds of things. So I'd like to remember where we had gotten to last time. We were talking about, okay, so Nick had been showing multi-replace, but I think what we realize is that, what is this? Gosh. Well, there are lots of good things here. All right, let's see how we're focusing this. We want to talk about, hold on here, let me just put this in the right place. Okay, oops, typo. Can't leave that there. Sorry, this is, okay. All right. So let's see, can we remember where we had gotten to last time? We were talking here about maybe talking about unification, and we were talking about this concept. Oh, okay. The general issue is you have we've been talking about, you have an expression. Given an expression, there are multiple transformations to do. And that can be done on it. And we can represent those by pattern matching, and multi-replace is an example of how to do that. Is that right? Is that what we're claiming here?
Right. That's right.
And in what sense is multi-replace the general case? What does multi-replace? I mean, you have to specify. What are you specifying when you do a replacement? In a replacement, you have to say where it is happening, how variables are bound, and what rule is being used. Is that a fair assessment? So, for example, if I say something like, I don't know, f of ABC, and I'm using the rule f of x double blank y blank goes to whatever. Oops, I used that rule. Then what I'm going to need to know is, well, actually, let's say I do something like g of that, comma, f of x, y, et cetera, et cetera, et cetera. This goes to, xx of x blank, x, y. Okay. Okay, so what I'm going to need to know, that is incredibly terrifying, that x, what on earth happened there? Oh my gosh. That would just be, okay. But in any case, when that transformation happens, how would I find out where the transformation happened? And I think, is it the case that Nick's multi-replace gives me that information? And where is the multi-replace code, by the way?
Oh, it's already in the repository. You can use the source function.
So wait, so is the replacement though, I mean, how do you specify where it replaced? You can't just do a single position specification because there might be further choices.
Exactly.
If you know what I mean.
Yes. So we can neither get that information out, nor can we put that information in. And that's part of where, that's part of something we've never needed, but we're going to need it now.
Well, maybe it's something about, you can return some association where, like, for each pattern, where you made a choice, you have the pattern as a key, and then as the value, you have the position that pattern was bound to, or something.
Nick, how do I use multi-replace? Oops, I definitely don't want that. Okay, so what Nick's thing is doing here is it's saying, what is it saying? It's saying that's the position at which this transformation is happening, but now it's not giving me additional binding information. But does it have a way to do that?
No, not directly. Well, there is a way to pass it on, but not extract it right now.
Okay.
Oh, but it's not just about knowing what X was bound, X underscore is bound to, because it's also like there might be, maybe list 1 is the position of the outermost sort of thing that was replaced, but there may have been further choices. There might be multiple replacements that you can do.
Right, like orderlessness, for example, could be there are multiple.
Sure. Yeah.
Because it's a replace list. That's why you have values in lists, because there can be multiple. Even at the single position, there may be multiple results.
Okay, so I mean, in this case here, if I were to do just this, for example, then that would be something that would be eligible for replace list.
Well, maybe not that, because it's only one.
Okay. But the difficulty here is that we're not tracking. Okay, so I mean, one issue then is tracking the information. Issue number 1, tracking information on transformations. And that's what we need to be able to do all the fancy stuff that we've done with multi-way systems like branch hill graphs and causal graphs and things, I think, is that we need to have that kind of tracking information. Is that true? Or is that, yeah, because we need to know, right now, all we know is we got this expression out. We do not know the lineage by which that expression was generated. And that's what we need to know, I believe.
Right, for the causal graph, especially.
Right. But so again, I want to kind of reiterate, we've got different objectives here. We've got things like find replace path, which I gather, and Roger, maybe you can speak to this. I saw some indication that Charles and the graph theory people were thinking about infinite graphs with generators. Is that right?
That came up from Julio because of beam search.
Okay.
So not specifically, but very big ones. I mean, like,
right,
outer core.
Okay, but I mean, so graphs generated by algorithms, out of core, maybe that's a different story than out of core graphs. Maybe not. Maybe it's a similar story, because if you have an out of core graph, you're sort of find replace.
You sort of can't look at the whole thing at once, type of thing. So
right, so you have to have an algorithm for deciding what to do next, which is similar to an algorithm for deciding what piece of graph to build next, so to speak.
Yeah, but big and out of core is decidable. Algorithmic stuff is not. They can be infinite. So I think it's rife with undecidability and stuff.
Well, it is, but even the out of core case, if you've got a petabyte-sized graph that's out of
finite.
I know, but this is one of these theoretical things. I mean, if you go and get lost in the wrong corner of the petabyte,
you're
unlikely to ever get found.
Not good. Yeah, don't do that.
Right. So, okay. So, I mean, what we've got here with okay. I mean, we've got this find replace path. Again, is one thing is.
I just wanted to kind of say something here that you may or may not be aware of. We have many sort of algorithmic rewrite systems, even though they're not presented as such classically. like Gaussian elimination is a rewrite system. And when you do row reduce, you do actually implicitly, or when you do LU decomposition, you do implicitly know in what order things happened.
Okay.
So I'm saying it's all reconstructible. Same thing for Grosvenor basis.
Okay, that's interesting. So I mean,
when you do polynomial reduce, you actually know exactly that's what it tells you, what that reduction is.
Okay, so computation tracing, your point is that things like row reduce, Grosvenor basis,
and LU decomposition, and so on. They give you the path.
Really? How does row reduce, for example, how does it give you? I thought it only gave you the final reduction.
No, row reduce does only give you the final reduction. You need to use LU decomposition if you want the whole thing.
Maybe I'm going to learn what LU decomposition does after all these years. Okay, what does it actually give you?
Well, first of all, it uses like let's say that you figured out the permutation order, so you're going to reorder your equations. So then it gives you a lower triangular and upper triangular matrix packed into one, which is something that we're going to revisit the packaging for. This is very efficient, but so the lower triangular matrix, it gives you the factors that matrix into a lower triangular, upper triangular matrix. And so if you're going to reduce, if you're going to solve later on, you solve first that lower triangular times a vector equals something, and that you can solve with forward substitution. That gives you the path. Then you do a next step, which is the upper triangle equals that vector.
Okay, the path is there, but the path is pretty encrypted.
Yes, exactly. Yeah,
okay.
Because most, the question is, do you need it? What do you need it for? Type things.
Right. I mean, another case of this, obviously.
And also, by the way, so when we compute Grosvenor basis, we don't get the transformation from the original set to the basis. But sometimes you actually need that transformation. Just like row reduce, just give the final result, or Grosvenor basis, just give the final result. And sometimes you need that, that transformation. So it's something for the future, which we
so we've got a version of this, which is the proof function of find equational proof. That is one of these things. It's not particularly useful because all you can really do with it is, take off the hold and just evaluate it. Right. So it isn't really, it is in principle, it is a path, but it is not a very usefully presented path. I mean, the only useful path that I'm aware of is the find path function, your path. Because where what you're dealing with is there a graph rather than computation steps.
Do you mean find shortest path or what path?
I think we have a find path function. Which
we do have find path. It's very general.
Okay, right, it's okay. We can say find shortest path, doesn't really matter. But my point is that there, the nodes in a graph.
And this is where optimization comes in. A lot of times, a lot of these functions have many solutions.
Yes.
Like that's what we're encountering up there now. There are many ways. Okay. Is there a best one? So you don't, because some of these things.
That's one case. That's the non-multi-computation way to think about this. Is there a best one? The whole point of this multi-computation idea is there are many other things you can look at other than just the best one.
Yeah, so you want other filters, probably.
Yes.
But you probably don't want all of them because that's like not practical.
No, you don't want all of them. That's the whole point. You don't want all of them. That is the point of this observer theory thing that we're trying to build, is what kinds of things could you want?
Yeah.
So you might want, the probability density, you might want across a space, you might want the best one, you might want various other things. But I think this is a relevant point. The nodes in a graph are much better defined than the stages in a computation. That is, and that's, when you can represent a computation as a graph, then it's very easy to say we got to this stage in the computation. But when the computation is something more like, a stage in transformation rules, it's much less obvious what you got to, if that makes sense. And, I suppose really the question is, can the computation be represented by a well-defined state? Okay, so for example, e.g. a string multi-way system absolutely can be. A string multi-way system, it's just the state is just a string. But in the general case, well, okay, be represented
In the
by
general
what?
case, it might be a whole stack.
Yeah, that's what I'm thinking. I think, yes, it can, because it's actually doing it, and they're called different things. They're called a stack, a continuation, or for lazy ML, a graph, which has a graph rewrite system to do it.
Right, but I mean, but that's also related to this fact you don't actually know which computation was done. The state, a state is just the static information on the result of the computation.
No, it's like when you do a recursion, where you're at in the middle type thing.
Yeah. Right. I mean, it's like
All right, but knowing the list of states doesn't necessarily tell you the list of choices that were made.
That's correct. It doesn't. The state is static information on the result of the computation, but not its provenance. Now, in the usual thing, in the usual case, usually the state is all you need to go forward. I believe that's right. That's kind of the,
that's sort of the definition of state, actually. If that's not the case, then it's not a state.
Fair enough. Fair enough. I mean, in other words, so we're denying the possibility that it could be history dependent, that it's this. Yeah, your point is, if it is history dependent, the state better contain a record of the history.
Yes.
Okay. But now, for the observer, okay, but the observer may care about more than just the state. E.g., the causal graph, et cetera, et cetera, et cetera.
So I'm getting so confused here, because there is a notion of observer, like in control systems, and its job is to get the state.
Oh gosh.
That's what Kalman did in the 60s. That's what an observer is.
Explain.
So if you have a system, physical system, you may not be able to measure everything about that physical system for practical reasons, etc.
Mm-hmm.
And can you infer the state from the things that you can measure? And yes, that sounds right, James Boyd. And what's used in practice is what's called actually an asymptotic observer, which is one that converges to the true state. It basically simulates the system in parallel and then looks at sort of how wrong is it, so it can converge into the true state. It converges very fast, mostly. That's what a Kalman filter is. It's an observer.
Right, but a Kalman filter, what is its internal representation? What is its internal information?
It's a system of constant coefficient differential equations.
So you're effectively fitting those to the observed data.
Yes.
And that is ultimate.
Yeah, you have feedback that causes it converge to the true state that you're trying to observe.
Okay, so this is state observers, which is a little different than what we're talking about, because we're talking about versus essentially multi-way observers. Okay, because what you're talking about is you have a given, you believe, okay, so
but the state that it's here, it summarizes the history. There is no more, if you see what I'm saying.
No, I understand that, but what I'm saying is, in one of our multi-way graphs, let's say something like this, every one of those nodes is a state. And the whole point of this multi-computation idea is that you allow the possibility that there are many states, many threads of time. You don't say there is a particular state, we just don't know it completely. You say there are actually many states running sort of in parallel in time. which is, I think, a different way of thinking about things. What you're saying here is, in control systems, there is a definite state of the world. Imagine there is a definite state of the world, but you don't know it.
Yes.
But you know only shadows of it.
Exactly. And it's super. I mean, this notion of observer, just so you know, it's immensely practical. I mean, it means that you can ship systems without too many sensors, or you don't need sensors in hostile environments where you can't have them and things like that. But you can still infer where the system is, what's going on inside the system.
Can you deduce enough about the system given a model? So for us, I mean, things like learn distribution and I mean, what are the analogous things? We've got what's the modern machine learning version of this? The modern machine learning version would be essentially a net train, wouldn't it? Or is that not right?
No, I mean, this goes on. It's a thing that learns all the time. Do you know what I'm saying? That there's feedback, so it sort of converges. It learns.
Okay, so what you're saying,
reinforcement learning or something.
Yeah, it's closer to that.
I mean, Roger has certainly made the claim that reinforcement learning is just feedback control.
Well, optimal control. You know, they're two. Yes.
Okay, so what this is doing, this is making something which, given, what the heck is this doing? So given
this,
go ahead.
This says, can
I think of it as inside its brain are a bunch of ODEs whose coefficients are getting tweaked based on the data it's seeing. And if you want to know other things about the system, you can you can just ask the brain kind of to run its ODEs and see what it produces. Is that the right kind of model? I mean, it's like
open up the notes. It's just I can't connect to what you're saying. So, oh shit, we need to update this. This is the old style. I'm sorry, this is not going to help us.
Okay, but in any case, let's just. I think this is not as relevant as it might be to this, other than that the words are the same. Because what you're saying here
is that you think about sort of physically how it's connected, okay? It's reading the inputs that goes to your system, whatever that is, your car or a robot.
Mm-hmm.
You know, your control inputs, the things that you can actually observe. It doesn't read the things that you cannot observe, like the wind blowing on the car. Mm-hmm. Those are called, that's treated as noise. It reads the output, what the car actually does, how it moves, sort of how the robot arm moves.
Mm-hmm.
But it doesn't say, but it also has a model that maybe you don't actually measure the output perfectly. So there's a measurement noise. So those are the two kinds of noises that are going on.
Right. I mean, this is awfully like reinforcement learning.
Yeah. And then given those two streams of data, and they don't stop, you know, there's not a function. There's streams, infinite streams of data. Can I get a good estimate of what the internal state is of the system?
Mm-hmm. Well, internal state requires a model.
I mean, yes, in our case, wouldn't it simply be in the multi-computational case, that is, the observer tries to determine if they have an accurate description of their foliation, right, as opposed to some single internal state. Because it's going to, yes, right?
But that's a much more complicated issue. I mean, that's not what this is. This is why multi-computation is a different story.
Yeah, exactly. Right.
I mean, this is a question of, you don't know, there may be many branches, you don't really care about the relationship between the branches, you are merely trying to nail the characteristics of your branch as well as you can, and you believe you're on a particular branch. Whereas the whole idea of this multi-computation thing is there are many branches that you can consider.
That's
and
right.
the observer is capable of aggregating multiple branches together. I mean, the observer is essentially coarse graining across many branches.
Yeah,
but
I mean, it's continuous, right? So it's not a discrete model like you're doing. But yes, I think what you're saying is roughly correct.
Right, and the continuous limit of multi-way systems is not well understood. We do not know what it is.
I see.
It is likely a very complicated thing. It is quite possibly, in the case of string rewriting systems, it is quite likely that the continuum limit is a string field theory where string is used in a different sense. Just to give a sense of how complicated it is. So, okay. So what we've got here, I mean, okay, we're still coming back to, okay, we've got the state of the system that in our model of computation is represented by a symbolic expression, right? So a state of the system in our world equals a symbolic expression, basically. That's what we're saying is going on. Now, you could have it, you could say, oh, it's real numbers, it's a function, whatever else, but we're saying the state of the system is a symbolic expression. What we do not have a representation of is the lineage of that symbolic expression. That's the thing that we need in the case of a proof, same thing we need in these paths and so on. How do we represent the lineage of a symbolic expression? Knowing that, okay, so the issue of representing lineage, one of the issues is, one issue is there is much shared lineage, and we don't want to represent it all of it separately. Does that make sense?
Aren't you basically thinking of this as the term rewrite system?
Yes.
So
yes.
Don't you just want the various terms and what rewrote it in each step?
I would say that if you have a function applied at each step, then this is relatively easy. A problem we have in find the question of proof is when we have the critical pair lemmas, the unifying of patterns and things like that. It's this merging of lines that gets difficult to express, and we don't have a way of expressing it in the proof function.
Critical pair are called S polynomials in the case of Grobner basis, and we don't output the mapping. You know, it's kind of like row reduce doesn't output sort of the transformation matrix how you got there.
Mm-hmm.
And
so it's the same.
It's the same, yeah.
So Nick has this nice way of thinking about this in terms of what we're calling bi-substitution, which is a sort of cleaner version of, I mean, it has to do with, okay, so I think we had examples here of substitution where you're going, where it is doing a traditional pattern match versus co-substitution, where it is using the fact that it is matching into a pattern and the pattern is being specialized to follow this form. If that makes sense. So the pattern is specialized by having X blank be specialized to B, and then this pattern can be applied. Does that make sense to people? And that appears to be a necessary piece of sort of the general term rewriting concept. I mean, it's worth remembering that things like, well, we actually don't know to what extent, maybe we do know and I don't know it, to what extent you can do term rewriting without bi-substitution and still eventually get to the same result. I think we have examples where you definitely cannot get to the same result. You get stuck. Pure substitution doesn't get you to the end. But Jose, I think this is what's happening in a critical pair lemma, is a transformation that is not one of our traditional. It is a bi-substitution as opposed, or a co-substitution as opposed to a substitution. So substitution is there is a pattern, and you are specializing the pattern in order to apply it to the expression. In co-substitution, you are specializing the expression to conform it to the pattern. Actually, that's a pretty good way to explain this. Does that make sense to people?
I do agree that we need something like this. I must admit I don't yet fully understand it.
Well, I've always thought that we need a function that we say below there, which is kind of what you're referring to, Stephen, which is the unification solver, which basically would give you solutions to those two, what's the solution to those two matching there that you have below?
Yes. Yes.
And that can be many.
Right, but that comes back to this very basic thing that we had up here. We don't have a way to output what is the binding. We only have an implicit way to output what is the binding for X and Y. I mean, the only way we have to output it is to use it in the result. Am I making sense? We have no.
Although, what's wrong with that? I don't know. I mean,
it's not bad.
And if you, yeah. And if you want to return other things too, you could use sow and reap, really.
Maybe, although that puts it in an undifferentiated vat of stuff. It doesn't give you. I mean, like for example,
although it's unclear how else you'd have it. But yeah, okay.
Well, that's the question. I mean, that's the question. How do we represent tracing of computations? That continues to be the question. I mean, back in 1990, we tried to solve this with the trace function, which was not very successful. It's incomprehensible, actually. I mean, I don't really know whether we've looked at.
I mean, couldn't that preferred term rewrite system be kind of like a debugger, do step by step?
No, because it's multi-way. See, that's the problem. The problem is,
but we implement something, right? If you want
we
to
implement
know
something. No, we implement something. But the whole point of this multi-computation idea,
to explore everything,
is to explore everything. Right? That's the whole.
Yeah.
That's the whole shebang. That's what's complicated. Right. So yes, I mean, the thing we've done, we have managed to slice through this horrendous complexity by just doing take the first pattern matching result and use it. Right. That's how our evaluator has worked forever. Right. What we're saying now is go beyond that and consider all possible evaluation paths. And then the concept of this observer thing is, given all possible evaluation paths, what do you look for from that whole collection of possible paths? One thing would be the path which does the best. Another thing would be the highest density of paths. Another thing would be something else. Does that make sense, Roger?
Yeah. Well, I'm just thinking of, I understand the research question.
Mm-hmm.
Have you thought about the sort of why you want to do that? In a production, I mean, in an application.
Okay, so for example, I mean, this is like an ensemble. I mean, you are basically doing the time history of an ensemble.
Mm-hmm.
Okay. Mostly in physics, people punt on that. They use the canonical ensemble, which is time independent, right? And they just say, on average, each branch will be weighted with eta minus beta h or whatever. Okay.
So, just so you know, you may not remember this, but when we did random processes,
mm-hmm.
we have a way to observe the ensemble. We have a thing called slice distribution.
I didn't know that at all.
We'll give a temporal slice of the full ensemble.
You mean that is very interesting. I had no idea.
It's very general.
What is an ensemble?
And it can give a multi-slice even.
An ensemble just means a collection of states. So, for example, a typical thing would be in a spin system. So
if you go to, to get a very concrete thing here.
Let me just answer the question of what an ensemble is, and then we'll come back to that. I mean, it's just the configuration of all possible states. Make sense?
Yeah, but to get a very concrete, practical, visual thing, go to random function. Okay, scroll down a little bit.
This is a function that does something very different.
There should be something better. Sorry?
No, nothing.
What did you say? The function.
I just said this is a function is very. I mean, you might expect random function is going to return you, plot or something.
Yes.
Yeah.
Goes for neat then. I just we should have this where you can see that we usually plot the whole ensemble too, but apparently we don't for the. Just simulate one here, because the random function is set up to give you a whole ensemble.
Yeah, that's
okay.
Right.
Yeah, or neat example should be probably many more.
Let's see.
I hope. Nah, forget it. But the ensemble is when you have many of them.
Okay, so now let me understand.
So
okay,
infinitely many of them. And so our temporal data is the data representation of the multi-way, of the full ensemble.
Okay, even though I've been trying to kill temporal data, it may turn out that it's actually exactly what we need. Is that what you're trying to tell me?
Yeah, do that for 100, okay? Crank that 10 up to 100 or something, or 1,000.
Okay, fine. There's an
Okay.
ensemble.
Right. Now, if you want to do slice distribution of Wiener process, okay, that can give, either can take temporal data or it can take the actual sort of mechanism. So they take that and now slice it at a particular time, like 1 or something.
Oops.
Yeah, 4.
What? No, I pressed the wrong button.
Okay.
Okay.
Don't do that.
Right, comma 4. Okay.
Yeah. Look at that. So
Wow.
at 4, we have a description
Wow.
of the ensemble there, and it's actually a distribution of values.
Can you do T? That would be very cool if you could do
Yes,
T
you
as
can.
well.
Yes, you can. Isn't that amazing?
That's amazing. So now
And
what
we can do
happens-
that for all of our random processes.
Well,
now you can give.
you mean analytically?
Well, I mean, there's a limit to how far you can go analytically, but slice distribution of a process of one or several T's, so you can do multi-slices too, and you get the multivariate distribution. But let's say a single T. Now, that is a random variable, and you can generate random variates from it. So you can call random variate on that slice distribution, happily.
I bet it's not very happy in this case.
No, this one has a parameter in it, so you need a concrete T for that to happen. Well, that one auto-evaluates. So obviously, yeah, that,
Yeah, right.
you know.
Okay, well, give me a more complicated process, random process.
Well, you know, like an Ito process maybe or something.
Okay, so the stationary distribution is what you would get. That is
that's the limited, you know, for
goes to
big,
infinity.
yeah. If it does have one, not all of them have one.
Okay. So here, just so I understand, what's a good example of a process here?
Well, you want something that's not too complicated, but you know, that one is pretty complicated, but it's okay.
Can you do fractional Brownian motion?
Not sure. I don't think so.
Okay, I might be asking too much.
Well,
maybe
it
just
wouldn't
like
be too
random
far.
walk.
It wouldn't be too far off from what we have, but it's probably one of the examples down there, but I don't want to.
Okay, but I had no idea we could have things with differentials like that. Is that a common thing that we've done elsewhere?
No, we've done it for Ito process and Stratonovich process.
No, but look at these differentials.
Yeah,
I've never
it's a
seen an
language.
expression.
It's a language. We defined a new symbolic language. We do that a lot of times for our solvers, you know?
Yeah, but why don't we allow that in differential equations, for example?
Because we don't know what to do with them in differential equations.
Why not? If dx of t, I mean, why is that equation?
Oh, I'm sorry. No. We do allow differentials there because, you know, the Wolfram Alpha team asked for it. So we do support it for dsolve.
So for dsolve, for example, I can say this.
I don't know if that works, but there's some version of that works. Oh.
The heck is that?
Well, I don't think that we're using that notation for it there, but there is a notation that allows
separate thing, which maybe somebody could make a note of. This is something we should look at, making that work. But that's very far away from the real topic here.
Yeah.
Okay, so I see Richard has put some interesting things in the chat. Let's look at that in a minute. Okay, so what you're saying here, you say I shouldn't use an Ito process, I should use something else.
Yeah, it's probably just like overcome. I mean, you can do that later, but just pick something a little simpler.
What
Would
would
you
you
like
like?
random walk? Random walk.
Well, I was wanting something which had a stationarity in the end. Okay.
Does that one have that? I don't know.
No, it doesn't. The random walk just gets bigger and bigger, just puffs and puffs out. Okay. And it's also got an analytical solution.
Yeah. So some of these guys have it. Some of these guys are stationary. Some are not. Okay. So, and we can tell.
Okay. So, but this
is a discrete time thing. Yeah. So
okay.
Random function of that, for instance.
And so there,
You have to say over what time interval, like 0 to, yeah. And then that will get you one path.
okay, so now if I say list line plot of that, why does that only give one?
Because you only asked for one. You said over what time horizon, but you didn't say that you wanted more than one instance in the random function. So if you say after 0 to 100, if you say that you want 100 of them, you'll get 100 of them.
Oh, I see. That had a time interval there.
Yeah.
Okay. Okay. Fine. That looks like it's becoming stationary.
It looks exceptionally stationary. Yes.
Okay. So now what
you can ask for from that process, you can ask for stationary distribution. I think it was.
What's happening here?
Well, look at that.
Okay, so I'm trying to understand where were we getting this from? So slice distribution, you're saying is the distribution of, okay, so the point is that the process here, a little bit of a difference to what we're doing. The process here.
But I think that's what you call a foliation or something.
Yes, it is, the slice. But what you're doing there, okay, can you pick other foliations other than the flat foliation?
You can do several T's, and now you get sort of, you look at two spots basically.
No, I understand that, but the issue is what we're dealing with is, okay, so the thing that you've got that is a big simplifying feature is that your states are defined by just individual numbers. Like the state of the Wiener process is the value at that position there.
Yeah.
I mean, like on the time vertical, you mean?
Yeah, yes. No, it's not on the time, on the vertical.
No, on the values. There's a sort of the value can be vectors, that's but yes. Yeah. You know, so it can be a little bit more, but basically, yes.
The value is numerical.
Yeah.
And
I mean, it can be a vector, it can be, but nothing more. It can be finite. Like Markov chains, it's sort of a finite, you know, symbolic value.
Perhaps this is an answer to the question of what, I mean, because, you know, like I've looked at length at things like, you know, nest graph, x goes to 2x, 1 plus x. Okay, starting with 1, going 5 steps. Okay. Now, how does that compare to what you're doing here? Let's say, do you get what I'm saying? So that's saying at every step, you've got these two possibilities. And I don't think you've got, in some sense, at every step here, you've got an infinite number of possibilities. And the steps, so sometimes you have a discrete process where you have it in steps.
Yeah. Take that ARMA process. Mm-hmm. It's basically a difference equation. It's a linear difference equation, you know, okay, where you drive it with white noise and you have a recurrence of the previous values, you know, and that recurrence is implicitly stated there where it says minus 0.3, 0.1.
Yep.
It says y of k plus 2 minus 0.3 y of k plus 1 plus 0.1 y of k equals 0.4 times u of k, which is just white noise. So that's just.
So hold on. So this is like saying linear recurrence of, you know, let's say it was minus 3, 1.
But linear recurrence, it doesn't have the right-hand side. See what I'm saying? It can't do filtering. It's not driven. It's just autonomous. See what I'm saying? There's no input to this thing. It's just initial value and a recurrence. And like in control systems, here there's stuff coming in.
Okay.
That's the initial values, yeah. There's stuff coming in that drives it all the time.
Okay. Okay, but let's, okay.
Sorry, isn't it the case that the paths in the statistical case are all independent? They don't interact with each other. While what you have in the graph is that there is this sort of recombination.
Exactly. Exactly. That's right.
Yeah,
that's right. That's right. That's right. Because the main thing that's happening here, which happens in term rewriting, is this notion of equivalence.
Yes. No, you don't think of them. You think of that there are many possible paths, but there is no notion of them talking, cross-talking, or anything like that.
This is the
Except-
difference between nest graph and nest tree.
Is there a nest? Okay, so let's look at what nest tree does in this case. I think it is. Yes, I think it is. I had forgotten the existence of nest tree. Beautiful. Right. A nest tree, how would we get from the nest tree to the nest graph?
Well, if you recognize, if those states are actual states, you could kind of recognize them and you would get a DAG.
Well,
You know what
yes,
I'm saying?
that's what we're getting here, is a DAG. But my question is, I'm just asking, in terms of trees, is there a way to go from that tree to that graph? Again, that would be a question for you.
We don't have
Let me try this
an
function,
operation that does that.
merge tree function.
What is it? Is there a, you're
It's a
saying,
resource,
from
resource
source
function.
Yeah.
merge tree?
Yeah.
And what do? I just feed it a tree?
Yes. You just feed it a tree.
Wow. Okay. And so, is that your function, Nick?
Right. Yes.
Did you make it for some purpose that is related to this?
How does it
Well,
decide?
for many purposes.
Okay.
How does it decide which to merge?
By subtree. Essentially, it just hashes each subtree and then merges by hash.
Oh,
You can specify any function that you can run on each subtree. And
this is
merge
like
by that
dagifying
function.
entire subtrees, not in individual nodes.
Yeah.
But why does
Individual
it
nodes,
have
you just
two-
do graph.
But why does
It's
it
just-
have two 4-4s?
It's just labels. It's just like have these labels that show that there are multiple branches merged there.
I see. But wait a minute. This graph is similar to, but not identical to this graph here.
Maybe it is. You just simple graph it.
Doesn't look to be identical. Perhaps I'm wrong, but it looks to be. I mean, we can do graph isomorphism, I guess. I'm not sure it's the same number of steps. Oh, it is actually. I'm predicting.
Why don't you just try the isomorphism?
Why there are several fours? So in the
Yeah, that's what I'm
satisfactory-
confused by.
Yeah, I would expect just a single four.
Now this is the difference whether you merge by subtree structure or just by the node. I think if you just want to merge by node, you just make a graph, right? Don't have a merge tree function. If you
Okay,
just-
wait a minute. So this is merging by subgraphs, but by merging by subtrees.
Yeah.
And then what you're saying is that to merge by node name, you are saying do that how?
Just by running graph on it, I think it works.
Ian, does that work? No.
No.
Because those tree nodes.
Actually, it used to work, and then we changed it so that you always get a tree graph out by using both the data and the position. Because before, if the data was in more than one position, then you could get a graph that's not a tree graph.
I see.
Yeah, and then now you just vertex.
But now
replace
there's
it
not
and-
but I guess
and
now that
drop
we've
the
made it where
second
everything's
part.
unique, we don't have that flexibility.
So Nick, what are you saying you do with this?
You just vertex replace and just drop the second part. So
Vertex
just
replace
vertex
what?
replace V goes to first V.
Oh, I see. In this thing here.
Yes.
Aha. Okay, and then we say simple graph on that. Well, I can't tell if it's the same, but it might be. %64. Isomorphic graphs. Ta-da! Cool. Okay, I think we're beginning to understand the relationship between these. Okay, but so big issue then is the equivalencing of paths is something not taken into account in the stochastic processes. Is that a fair statement? Now let's see. Let's look at these comments that Richard has here. My gosh, what is this? What on earth? Okay. But on the issue of evaluation strategy, i.e. observer reference frame construction. Oh yeah, sorry, I wanted to ask Roger here. So it is still the case that we could imagine our equivalent of a reference frame or a foliation by saying in your sampling here, instead of saying time, for you, it is natural to slice in your slice distribution, to slice values at a fixed time.
Yeah.
Right? Yeah. The generic value, generic slice distribution is all values at fixed time.
Yes.
Different,
or several time, so
okay, at fixed time or multiple times.
Yeah.
Okay. So different foliation / reference frame would be, distribution in which at different values, for different values, you are sampling at different times. Now, maybe nobody ever cares about that. But let's talk about this in the context. Okay, so these things here could be thought of more like execution graphs for some kind of parallel computation. And in that case, this question about what does it mean, what does the simultaneity surface mean, is a more complicated question, and is much less obvious that you always want to sample, that there's even a notion of sampling everything at a fixed time, if that makes sense.
Absolutely. Not clear.
But now, is there an analog of that in stochastic processes?
Not that I know of.
I mean, one could certainly imagine a relativistic stochastic process. This would be a Jose kind of question of imagine a random walk. I've never thought about this. A relativistic random walk. What is the theory of the relativistic random walk? Would be the question here.
I don't have an answer for that immediately.
I mean, I long ago, I worked on relativistic kinetic theory, and even that was pretty complicated. For example, like the notion of the maybe this has been figured out, the notion of the relativistic transformation for temperature, which is not unrelated to this, because what you're asking for is, do you know if that was ever figured out, relativistic transformation for temperature, Jose?
It was a big discussion in the early times of special relativity, and there are several theories, but the consensus on how it's treated in general is by always going to the rest frame. We always refer to statistical properties in the rest frame, and that avoids completely the problem because there is a unique preferred observer.
Right, like the cosmic microwave background.
Mm-hmm.
Even though the universe wasn't supposed to have a preferred frame, there is a temperature for the cosmic microwave background in the preferred frame of the universe.
Mm-hmm.
Okay, anyway, that seems to be a sideshow. But okay, but coming back, let's see. Richard is commenting, evaluation strategy, observer reference frame construction. Rewrite tower. What is this? This is oh my gosh. You see that the problem is, so this is a particular rewrite language. You know, I think, and I probably nobody here knows these folk, the people that we've been interacting with in France who've been doing these things, these tracelets and so on, they may have something relevant to all of this, although I didn't really understand how that stuff works. Okay, so this is an example, but this is exactly what we don't want. That is a word there. That's what we effectively have in our proof. You know, that's what you typically have in a proof. Is it's full of words.
But they say that that's kind of the words say the rule, basically, right? Or some.
Yes, the words say what is being done.
Yeah.
And yeah, right. So I mean, I think this is right. Okay, well, the user-defined strategy language. What is the strategy for applying rules? Because that's one of the big questions, right? Is the sort of the big question is you know, which rule to apply when, right? And that's where we get into our tree traversal order, you know, where we've got that's this thing where we're dealing with all of these lovely things here, right? You know, all this stuff. But we need to do better. We need to have a more, you know, this is all just named strategies. See what I'm saying? And the question is, what's a, you know, each one of these, go ahead.
I don't think these are quite strategies for rewrite rules, because here you're like just hopping around between all the different branches.
No, these are rewrite rule things, because if you imagine that the tree is a multi-way graph that represents possible rewrites. So for example, imagine that I have a nest graph where I have x goes to f of x comma g of x. Okay, then what this is doing, and let's say that starts with an x or something, and it goes 4 steps, and then we label those. I claim that this is an evaluation order story. That exactly.
But the point about traversal order is it's giving you an order to visit every single one of these nodes.
I see what you're saying.
Really has nothing to do with starting from the root and going down.
And
that was a thought I had earlier when you mentioned with multi-way systems, you're mostly interested in either very large cases or infinite cases. But for trees, it's like you have a very finite thing, and you do want to like traverse the whole thing and get information.
Okay, let me understand the analogy then, which I don't understand here, to the combinator case. Let me just pull up some combinators. Okay, so here, okay, so these are combinators, and I mean, confusingly, that is a single combinator tree, and this represents a possible rewrite sequence for the combinator. And what you're doing here is you're selecting different parts of the tree on which to do the rewriting. Unfortunately, we've got true trees running around here.
So you're thinking of using the traversal order to somehow be the strategy for finding where in the expression to apply the rewrite.
Yes, I think that's correct.
I see.
Right. Which is, I mean, and so here
preferences to some positions in the rewrites than others.
Right, but now the place where we've got a second tree going on is that all possible rewrite orders are represented by this multi-way graph. So in other words, here, if we think of F and G as two rewrites, this tree here is representing all possible rewrite orders. So when we say we are picking, so you're right, it's a different tree we're talking about, right? So wherever I probably have it here. Come on, I've got this somewhere. Yeah, okay, so here we go. So this is a particular, this is one rewrite order will traverse the multi-way graph like that. Another one will traverse it like this. I think I've got somewhere here, I've probably got the comparison of leftmost, outermost, leftmost, innermost, et cetera, et cetera, et cetera.
Right. It's like because of the way you're doing replacements on expressions in a given traversal order. And so the different traversal orders give you different like paths in the multi-way system.
That's correct.
But
that's correct. But
traversal order question isn't really a traversal order in the multi-way system. You're not like skipping around willy-nilly in the multi-way system.
But you also want to do that. So we've got, this is very confusing.
right,
I mean,
right.
it's very confusing. There's two different things going on. Okay, so two different tree traversal. Case one, in the expression that is the state. Where do you do the rewrite? Oh boy, this is confusing. And that,
it's like,
given
what order do you look for terms to rewrite?
That's correct. And this gives you, choosing an order gives you a single path through the multi-way system.
Yes.
Okay, so another case is 2, looking at the multi-way system and growing the multi-way graph. In what order do you grow the graph?
Aren't there like two completely different trees? There's the expression tree, and then there is sort of, the tree where every node is an expression.
Yes, this is the exact point that I have been confused about since 1980.
Okay.
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 Let me describe what the issue is again. Okay. We have in our evaluator 2 kinds of recursion. Kind number 1, recursion through an expression tree to decide where to look at next. Okay. Recursion number 2 is reevaluation recursion. Do you see what I'm saying?
Yeah.
Jose pointed out that our documentation calls the first kind iteration.
The first kind, or is it the second kind? No, it's the second kind, isn't it?
Oriel, do you remember, Jose?
So iteration is evaluating the next thing in the expression, like going through the various arguments. And this is represented in trace in a flat list. And recursion is reevaluating the same thing again. And this is represented by a next level of list.
In what? In trace.
In trace.
Isn't this also, I thought that the thing with like iteration limit and so on is basically it was tail recursion.
Actually, that's what I thought too.
Yeah. Right. I mean, I think there's a difference between if I say x equals x plus 1, I will hit, oh gosh, I thought I was going to hit the iteration limit there. And if I do this.
No, right, it's recursion because it's a nested thing.
Right. But this has been, okay. What's a minimal example of trace that isn't just totally ridiculous? Is there I mean, if I define, let's say I define let's do this. If I say x plus f of x minus 1, yeah?
Sorry, can you go to the reference page of evaluation? I put the link in the chat.
Okay. Okay, I will, just a second. Let me just try this. Trace of f of 5. Oh my gosh, what is this? How can I visualize this? What can I do with this?
We're going to support this in expression tree, but I don't know what we can do right now.
Can we make this into a tree right now? Is this even a tree? Okay, basic question.
Just
what
looking at the nested lists, and so you'd see the siblings are iteration and the descendants are recursion.
Really?
So f of 5 evaluates to 5 plus f of 5 minus 1, so they're siblings.
Yes, but I don't believe you. I think that's only going to work. That's the problem, that you've actually got two recursions going on. You are talking about in your tree, the recursion in the tree is going to be recursive recursion, so to speak. That is f of 5 going to f of 4, as opposed to if I made this expression more complicated and you had to also do recursion through the expression, so to speak. That's a different kind of recursion.
Yep.
Which I don't think one's representing well there. Okay, let's look at the.
So go to the very end of this page.
The which?
Go to the end of this page. Yes, here, global control of evaluation.
I think I wrote this in like 1987.
Right. So tree traversal order is like a third point to this, I think.
I think this mostly represents my state of leads to evaluation chains in which successive expressions are obtained by the application of various transformation rules.
Which sounds like tail recursion.
Yeah.
Yes. I mean, I believe I have been confused about this for more than 40 years. So just to...
Which to me is the kind of state, like it's a fixed size state type thing, to me.
Which?
The tail recursion business. You can...
Possibly so. Right. I mean, okay. But okay. We've got various issues here. In the expression that is the state, where do you do the rewrite? How do we specify that? And then in what order do you grow the graph? How do we specify that? In this case, where do you do the rewrite? We could specify that, one form of specification would be the language of tree traversal order. And in a sense, tree traversal order, i.e., taking the first, the first rewrite in the traversal order. Am I making sense? That's how we'd be using
first rewrite, or you could apply all of the rewrites in the specific order.
Well, you could do but the problem is,
I think a given order, you still have multiple different things you care about, like apply the first rule you find or apply all rules. But
I agree. So are you taking the first rewrite? So e.g., in the physics project, okay, we have this notion of generational states. Generational states are, okay, so generational states are the analog of string replace. Okay, so what do I mean by that? If I do string replace here, and I say I've got A, B, B, X, A, B, okay? And I say AB goes to, XXX or something, okay? Notice it did that 3 times, okay? It is not obvious that it would do that 3 times. It is using, what it is doing is it is trying to fit in, okay, so there I can do that and I'll see all of those. Now notice if I do this, if I say string replace of AB, actually, let me do this.
Honestly, pretty confusing that string replace returns an output that isn't an element of string replace list.
It is confusing. I agree. It is confusing. Now look at that. Yes. Okay. So a good example here. By the way, that should probably be in the possible issues section. Okay. So of string replace and string replace list. Okay. So
doesn't that mean that string replace is kind of replace repeated?
It is. It is. It is doing what we would call in the physics project the generational states.
I mean, it's even worse than replace repeated though, because it's like replace repeated. It's replace all. It's not even replace.
Yes. Okay. So it is the analog of replace all, which also has the feature that if I say ABC here, And now I say replace all of f of x blank blank triple blank y triple blank arrow, x, y, right? It's just going to do one case. What am I saying here? That's not.
I think using something with pattern sequence would have maybe made it more, well, whatever. Yeah.
No, but
I guess my point is replace all implicitly has some traversal order.
It does.
Be interested in that same operation just with a different traversal order.
No, but okay, this is where it's even more confusing, okay? Because one thing you might do in a multi-way system, every edge in a multi-way system corresponds to a single replacement happening. Okay, so for example, in the string replace here, those are 3 replacements in the multi-way system. Let me show you that. Okay, so let's take this and let's say down here, let's say resource function and let's give that, whoops, I didn't mean that rule, I meant that rule. And let's say 4 steps. Okay. So that's the multi-way graph. So the multi-way graph better be doing the same thing that string replace list does, right? At the first level, it's doing all those string replace lists. That makes sense to everybody? But then it keeps going, doing more replace lists, and eventually winds up in this state, which in this case is the same as string replace. Okay, although that might not always be. In this case, there was a, so let's say I take the initial condition to be, let's say what I did here was I say AA goes to X here.
Is it possible to get something with string replace that you couldn't get by doing sequential rewrites?
No, it's not. You have to be able to, it is a sequential rewriter. Okay, so let's say, is that confusing? Let's see. Oh, let me do this case here. Okay, so this is fairly obvious. But now in this particular case, string replace is going to give, what is it going to give actually? Okay, who can guess which of these it's going to give? I have a guess. I'm going to guess it's going to give that one. Yes, I'm right. Okay. Is this making sense to people? What's going on here? Roger,
Yes,
can you?
It should be called string replace all, but yes.
Yeah.
Why do you say all? Isn't it
Going
like
left to right?
repeated? It does a replacement and then it does it again. It repeats it.
No, that's what replace all does.
Well, I mean,
Both are true.
both
Both are true in this case. That's what's so confusing.
Yeah, but I would guess that if you gave it some cyclical thing where replace repeated would loop forever, this will not.
I think you're right. Yes, I think you're right.
Yes, but so okay. So there are multiple things here. I mean, first of all, there's these different forms of recursion, and then there is tracking what happened. Like in this case here, let's say you go to XAX here. Okay, how do we write? What we would like to do is to write some representation of a path we followed to get there. What would that representation be? Right now, it will be a string replace part or something, a series of string replace parts. Does that make sense?
I think as long as the siblings are always in a fixed order, that you can just use a position spec for a DAG. So you just say 3-1.
I think that's a not a chance type story. I cannot believe that there's a way to label these DAGs.
But what you have as nodes here are what I would call states. You know,
And we would call them states too.
okay. But don't
They
you
are
think
states.
that but wouldn't that be a good, you know, like state, like a sequence of states, you know, and maybe what you did to get from one to the other?
But that's the point, what you did to get from one to the other.
Yeah.
That's the point. That's specifying that. So we have a way of representing that in multi-way systems that's not wonderful. I mean, we have this notion in multi-way systems of a state decomposition function, an event decomposition function, and so on. Because an event here is, I rewrote that first AA. So let me show you what an actual representation of that. What's it called? Evolution events graph. There we go. Okay, so those are the events.
I see.
Oh
yeah.
Boy, that's confusing. Look at this one here. Okay, this is a case where there are two possible events. Well, that one has four possible events. The events are essentially the output of string replace list. Okay, so a representation which would be okay is to say you go from this state to this event to this state to this event. Now,
do you ever care about sort of more than one event resulting in the same state?
More than one event. Yes, so absolutely.
Two yellow boxes going to the same blue box.
Absolutely, critically so. Like here, that's a merge. That's all to do with confluence and so on. Yes, you absolutely do. Now, the other thing is, in this picture, one is only showing a single state going to multiple states, okay? We also have this notion of token event graphs, where you can have multiple tokens that can go into an event. So in these events, every event here has just one input. You know, one input, one output. But you don't have to have that be the case. You can have an event that has multiple inputs and multiple outputs.
But isn't it fairly obvious how this corresponds to expressions? You know, the blue boxes are expressions.
Yes, they are. Yes, that's right.
You know, and the yellow ones are, how do you get there? You know, and you list both where and what, basically. Look, that notation that you have there?
Yes, that's correct. Look, I mean, the point is that with the expressions, we really view the expressions as being collections of tokens. And those tokens, the events, ingest collections of tokens. So for example, for any given expression, there may be multiple, let's think about this. So there are multiple ways to break it into tokens. No, I'm sorry. That like for a string like this, the tokens are the characters, and it's different collections of those characters that can be involved in the event. But I mean, so again, the problem is, how do we represent? You know, what's a good way to represent that event? Okay, so in the case of, does somebody remember how we're doing it in multi-way systems? I think.
I mean, what's so confusing here? If the blue boxes are themselves trees, like expressions are trees.
Absolutely.
Okay.
Yeah.
Then the yellow boxes would be kind of like a subtree.
That's correct.
Tree.
That's correct.
You know,
exactly. So
I mean, that's sort of we need simplification.
Well, this is. I probably got pictures here. I mean, this is. Where is it? Yes, exactly. This is right. I mean, in one of these things here, that's for combinators. Okay, every node here is a tree.
Yeah, makes sense, because that is the analog then.
Yeah. Yes, right. I mean, this combinator thing is a minimal version of the kind of thing we're dealing with expressions. And so again, to describe a single path through the multi-way graph, you can do that by giving a strategy for which element of the combinator you rewrite, and it's only one, which confusingly is not the same. But as Ian was pointing out, it doesn't have to be only one. Like string replace doesn't do just one rewrite. String replace is doing all the ones that will fit. Okay, so the strategy, and I believe your does your tree traversal order, I'm trying to remember now, tree traversal order is simply an ordering. And so there's another parameter you would have to give, which is how many of the elements from the tree traversal order do you actually do in a particular step? Oh gosh, no, it's more complicated than that, because the things you can do together at one step are not all possible.
Like, let's say there was like a first case, like select first for trees.
Mm-hmm.
You could specify a traversal order, and that'll affect which thing is the first thing you get.
That's correct.
But if you're doing a tree map, then you're not, it's just a different operation, but it still has a tree traversal order.
I understand, but if you say select 3 things, it is not self-evident that your strategy will allow you to have 3 distinct things selected. See, it could step on its own toes.
That's implemented now. You do tree select, and you can say, I want the first 3, and then you can say a traversal order, and it gives you the first 3 that you find in that traversal order.
In some immutable sense, because those things could be overlapping. Right?
Well, they're not changing in tree select.
I know. In some immutable sense, I'm saying. But were those things to be rewrites, you would be toast at that point. Right? It's all easier if there's only one thing you're returning that you can then rewrite, because one is always independent of everything else in some sense. Right? But as soon as you're rewriting 2 things, there's the problem of what if those 2 things overlap?
Right.
Actually, note that our string replace doesn't have the overlaps option. I was looking at that. Some other string functions do, but not that one.
That's really weird.
So
oh no, but what could it possibly do? If it had overlaps to true, what would it possibly do?
Well, in these 5 A's, it's looking at replacing the first 2 and the second 2, 3 and 4.
Mm-hmm.
And it could return like XXXX, because there are 4 pairs of A's in 5 A's, or 3 pairs of A's in 4 A's.
I see. So you're saying at the first step, so let's just understand what that, okay, so if we say string, what will we do? We're saying string cases, for example.
So it has disjoint matches, basically. It can never.
Yes, that's correct. It is a disjoint matching thing. So if I string cases AA, how the heck do I do this? I say, let's say X blank, and then overlaps goes to true. Okay, whereas if I say overlaps goes to false, these are good documentation examples, if nothing else. Okay, whereas,
right. So string replace is only following the second.
I understand, because string replace for the first would reuse an A in the replacements, which it's refusing to do. Because none of our other replacement functions can ever reuse a part in a replacement.
Right, but your multi-way system is actually doing overlaps true. That's why it has 4.
That's correct, because any given path never steps on its own toes, but 2 different paths can step on each other's toes, so to speak. I have another question. There's perhaps a Roger question or others. Okay, so let's see. When we think about GPUs and parallel computations and things like this, these issues obviously come up of what do you do first. I mean, like in operations on arrays.
Yeah.
There's got to be exactly issues like this.
Yes. Yes. I mean, the question is how you split problems and where is a good split so there aren't issues, so many issues like this, because it drags down performance.
Well, so
The
you
things
say.
the things that we have built in mostly deals with when they're independent, like in parallel problems.
I know, right. Richard's commenting for GPUs that causal dependence analysis via the causal graph could help. Yeah, I agree, because in this question of what
like a modern CPU does some things pretty amazing, because you have these superscalar processors, right? And so they ingest something like 500 instructions these days. Then they compute the dependence graph. And then they schedule them on separate functional units. And then, for the most part, the programming model that we provide, we want to imitate as if they were happening sequentially. So we want to what's called retire them or return them in the correct order.
Okay,
but
so
it does that on the fly, actually.
Right, but so here's the point, I think. Right now, let's say we're doing Wolfram language computations on a random CPU, okay? The definition of Wolfram language today is that it follows one path here. Okay, we've probably got pictures like this one here. This is the path it follows in the multi-rate graph, okay? But it could be the case that that path might not even be the most efficient one to implement on your hardware. And you might not even care that it followed that particular path. If it was the case that many paths get led to statistically similar, let's say you're doing image decompression, for example. And yes, there are multiple paths, and yes, the pixels are a little bit different, but it doesn't really make any difference to follow a different path. I don't believe there's any technology right now that, that seems like a thing. That's like using, right? Like what you're describing, Roger, is you are making sure that the computation can be done in exactly the order it was supposed to be done in.
Yeah, and it's pretty local. I mean, 500 is impressive, but it's still pretty local. To what I'm saying, but they're able to do it like on the fly and very fast, right? If we can do something one level above that, that's more global than that sort of instruction level, basically, much more.
Right. Let's see. Richard has a few comments here. I want to look at these. Let's see. There's comments about decidability. Let's see. Richard, do you want to say something rather than having me be confused here? Go ahead.
Sure. The first point was really about sort of evaluation strategy control via, a sort of reflective language. So within the system itself. And that's something that this ELAN language, it sort of treats the strategies as sort of first-class citizens. And then the second reference I pasted, well, actually I pasted 3, but the second is talking about this sort of tower of, so you can have sort of strategies on top of strategies and so forth.
How do they represent a strategy? That's the real question. What is the, in something like our symbolic language, all we've been able to do is the extremely lame thing of saying we have these, named strategies. How do you make a language of strategies?
And you should provide it as much information as possible. So for example, you're talking about the sort of application position information for each state through time from the initial state. That's something you would want. You kind of want full information, and then something which gives you a kind of essentially a sort of decision function over the sort of, so I guess it's like state evolution function. So the normal forms would, given the sort of future states would return, as a simple example, just true or false. And so that would give you the set of future states. Well, it's a bit more than that. It's not. Yeah, I suppose it is. It's just a set of future states for a given state.
Right. The
but
problem
then this.
Yeah.
Sorry, go ahead.
No, I mean, the challenge which I'm trying to understand is, what is a reasonable human understandable language that can parameterize evaluation strategies? That's the part.
So they give some they give some elementary strategies, and then they sort of compose user-defined strategies out of these elementary strategies. So that's the approach that's taken in this ELAN language. But I guess, I mean, in the same sense that sort of Mathematica is, higher order conditional term rewriting. I mean, that's the characterization of Mathematica from who's it, Bruno Buchberger. You can sort of carry that idea to the strategy language itself.
Right, but that's the part that I'm not understanding, is like, what would be a primitive in the strategy language? I mean, like here we've got, go ahead.
I mean, they give some examples about, so here it says, non-determinism is handled with two operators, don't care, standing for don't care choose, and don't know choose. So I guess they have this notion of controlling the non-determinism. So at certain points, you either choose between, well, they call it don't care choose and don't know choose. I'm not really sure on the details, but presumably this sort of accumulation of all those decisions throughout your sort of history path, then that's sort of constraining the set of final normal forms. And in the paper, they talk about this sort of determinism mode inference. So given a strategy specification, then you can, because they have this compiler as well. So given a strategy, you can determine whether it's deterministic, semi-deterministic, non-deterministic, and can perform sort of termination analysis.
Right. So all that's saying is, when you say deterministic, non-deterministic, whatever, we'll be saying, like, here's a multi-way graph. With this particular strategy, do you get one path or do you get many? That's the decision of whether it's multi. I mean, yes, I think I understand that the issue here and the challenge, my 40-year challenge here, is to make a language which is actually comprehensible and useful, that can parameterize the strategies. And the part of this that is now tantalizing is because of the relationship between this and reference frames in physics. In physics, we have all kinds of, inertial frames and boosted frames and accelerating frames and things like that. And those are essentially evaluation orders. They're representations of some kind of evaluation order thing. We've got these different cases. We've got depth first, breadth first. We've got leftmost, outermost, etc. These are a whole collection of named, evaluation strategies. The question is, what is I mean, you could as well say, let's just do all our computations by naming the three kinds of things, plus, times, divide, whatever. Those are the only computations we want to do. But the neat thing about Turing machines was the idea that you could essentially parameterize any computation. And of course, Turing machines as such were a lousy parameterization. And then we had to, wait for higher level languages to have reasonable parameterizations. Even lambda calculus would be better. But so my question is, what is the reasonable parameterization of a high level description of evaluation strategies? Because it's a higher order problem than describing a computation, I think. In other words, instead of describing, you rewrite this to that, you're saying, of all possible rewrites, which ones do you choose to do? Which I don't know.
I think the order is also important as well. So yeah, it's not just a set; it's a sort of ordered set. And I mean, presumably you could just do that with, like the lambda calculus, or as a hack, sort of encode the states as a sort of binary representation and use something like binary lambda calculus.
Yes,
it's not interpretable, but it's.
The problem is this. The problem is, how do you make the connection with what humans can understand? In other words, being able to say which branch in the multi-way system. Okay, two problems. In the multi-way system, things are being made dynamically. So you don't get to say, in other words, you don't know the structure of the multi-way system until you've computed to that stage in the multi-way system. And once you have the structure, you can absolutely say, take the third fork in this multi-way system, but you don't know in at the beginning, you don't even know that there is a third fork at this point. You have to compute to that point. If you then say, and it isn't an interesting strategy. Well, the strategy that we're taking in our evaluator is essentially take the first fork. In all cases, just take the first one.
I think that's combining things again. In the multi-way system, the nodes are whole trees, right? So
yes, but I'm saying that you can do that. Look, a typical case would
take
be
the first fork in the tree, which is itself a single node in a multi-way system, and that itself gives you a path in the multi-way system. But I don't think that's like the first path that you see in the
I am indeed conflating things, because I mean it's like you evaluate Fibonacci, right? And you've got like for example, we can do that if we do, just to understand how this relates. So let's imagine that we have, let's see, can we do this? How do we do this? Help me, Nick. Do you know how to do this? What am I going to do? I'm doing I'm trying to compute Fibonacci using, I say if x less than 2, 1, otherwise I want help. What am I doing here? Do I want a list?
Well, NestGraph doesn't have access to 2 steps before, right? Or you can give it, you can have it so that each step you have a list of 2 things.
This looks right, Stephen.
It's like backwards. Yeah.
Do I do from this 3 steps? Okay, let me just but this is
nest tree.
That's what I want, right? So this one here, I say vertex labels. This is an optimized Fibonacci.
Mm-hmm.
Is that right? What am I doing here? I've got 5.
Although I thought NestGraph internally didn't assume determinism, unless that's been changed.
I think it was changed. But what am I even doing here? What is this doing? This is not an actual Fibonacci. I'm now confused about how I'm
showing you. F of 6 depends on F of 5 and F of 7.
Okay. So here
I messed those numbers up.
Help. What am I doing here?
Replace list 5 with just 5.
Return function. Oh, does this have to be a list here?
Oh, yeah.
Okay, what on earth am I seeing here? What are those zeros?
If you were going to compute Fibonacci of 5, then you would naively do Fibonacci of 4 plus Fibonacci of 3.
Okay, so this is in fact a Fibonacci tree. Is that a true statement?
This is just the downward portion, and then Fibonacci is the upwards portion, where you're actually adding the results from each branch.
Okay.
Well, I see, instead of list 1, do empty list.
Where? Here? Okay. Oh, is that a Fibonacci tree now?
Yeah, but it's not doing the weird thing at the end where it keeps going.
Okay, but so I mean the challenge here again is there a language, and Richard is commenting on this don't care and another primitive, what was the other one? I forget what the other one was, but that's a possible way to represent some.
They give an example further down the paper, which is a little chess game, and they show how they sort of control the search space exploration. So it's kind of an intuitive example. Section 3, non-determinism in ELAN. Sorry, I think you have the wrong paper. The paper is the non-deterministic computations in ELAN, which was, I think, the first link I sent in the It's actually the second link in the chat, the message which starts, but on the issue of evaluation strategy.
Okay.
And then section 3, non-determinism. And the,
yeah, the wrong thing. Okay.
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 Yeah.
All right.
So I'll let you look at it.
Okay. So there are multiple things that can happen. Okay.
Well, I mean, in the paragraph just under the chessboards, they say, yeah, they give, yeah. So there you go.
Yeah. This part I understand. The trouble is, I mean, that's saying very locally what can happen. And that's like giving the replacement function in the multi-way system, which, this is effectively defining a multi-way system, I think. This is not defining this is defining the whole multi-way system, I believe. Not defining in what order you will sort of,
doesn't the path that you take in the multi-way system, like if we're thinking of having a strategy for picking a path, doesn't that strategy depend on how you're representing states as nodes? Like strategies are going to be described differently if you're describing string rewriting or expression rewriting.
Perhaps, but I mean, a strategy, look, at some level, a strategy, it's like a proof, okay? Where you can write out the path that you follow in the multi-way graph. Okay, the path in the multi-way graph is a proof.
But
if you say
the strategy would be more like a tactic in proof.
I think yes. So tell us about how those work. How are those specified?
So tactics is like a sketch in the proof. You just give indications of how the proof should proceed to a point that the computer can fill in the gaps.
Right, but how do you give those tactics? They're usually named tactics, aren't they?
They're named, yes. You would say, now use this big theorem, now use induction, now use...
You see, this is the thing. This is what's driving me crazy. We got the same thing all over the place. We got the same thing in general relativity. It's named solutions to the Einstein equations. It's like, it's not...
Also, when you compute, for instance, we'll take a Grosvenor basis, okay? Which is like theorem proving. You're going to find the critical pairs and all of that. But that's what all the research has been about. The only thing you can give in, which is too much freedom for most people, is variable orderings. And there's way more than n factorial possible variable orderings.
Right. And that's what degree lexicographic and all these kinds of things come up.
Yes. And there's sort of n factorial lexicographic orderings, but there are many more orderings than that.
Right.
But inside, it's using a tactic like Jose describes. It's and those are those are sort of differently efficient ways of computing the end result. And
right.
And the ordering matters, but there's also other stuff that you can't control, which is sort of the implementation of the algorithm. It's not user, unless you implement it.
Okay, but the basic point here.
And same thing happens, by the way, in a some way simpler context, but they say sparse, actually even dense linear equation solving.
Yes.
So von Neumann and Turing and others, investigated the numerical stability of Gaussian elimination.
Right.
And they found out that you could deploy a tactic, which they call pivoting, that
right.
would sort of, basically make it, stable.
Right.
And, and right now, like our LU decomposition, and which is the norm in all of linear algebra, is use what's called partial pivoting, which means you pivot the order of equations, but not the order of variables.
You know what's driving me crazy? This is the same problem. I mean, it's one of these cases where the same problem is just showing up in all these different fields.
Yeah, and then if you go to the next scale, which is sort of sparse linear equations, there's something called orderings. You try to reorder the equations and variables so that you minimize fill-in, because you don't want to go from a sparse
right.
matrix that's 1,000,000 by 1,000,000 to one that's dense. That's like
right.
bad. And so there are things like Cuthill McGee, or they're named, because they need to be cheap.
I knew Betty Cuthill. She was a charming person. Yeah, okay. Please go on.
Yeah, there's a whole bunch named ones, and people have investigated. If you spend more time on trying to figure out the strategy, are you going to win? And the sad result is that, no, you won't, because you'll chew up too much time trying to figure out the smart strategy and you won't win.
Right. Okay, but what we're learning from all these examples, the fact that every one of these strategies has, or tactics or whatever, has a name, means we haven't solved the Turing machine-like problem.
Perhaps when the space of possibilities is so large and complex, naming the successful ones is the only way to go.
Well, yeah.
There's a similar thing of picking variable orders for BDDs, for Boolean functions. They're n factorial possible ones. You can't.
Okay, so Jose, what would you say in general relativity, for example, about or even in special relativity, about reference frames? They're again named.
Well, in special relativity, you can parameterize them via Lorentz transformations. But in general relativity, yes, you name the gauge conditions to select particular nice coordinates. Yes, indeed.
And is there anything beyond that? I mean, there are parameterized families, but that's about it.
Yes, I mean, there are the space of foliations is absolutely infinite, right? So you can slice spacetimes in some very many ways that most of them are completely useless. So you just give yourself techniques to find them, like harmonic coordinates and things like that. So which are successfully.
See, this is what old.
But here is what I found that seemed to be successful in all these cases that I enumerated, and also for modern superscalar CPUs, is to basically adapt and do it sort of locally and kind of real time. So, for instance, for Grosvenor bases, what you can do is that you figure out how to reorder them as you go, as you learn more.
I understand. It's the same thing. Automated theorem proving. You could imagine doing the same thing.
Yeah, the same thing happens with basically, the way you figure out pivot sequences as you go. You've eliminated this far. Now what's the pivot? And you investigate your local situation right there.
Right.
And the similar things. There was the breakthrough for BDDs, and that's called. It has a name, but it allows you to sort of reorder kind of as you go.
Okay, but just to roll the clock back to 1936 for a second. Imagine, we're talking about real numbers, and people are saying, oh, we got all these real numbers. There are ones named algebraic numbers, and there are ones named this, and there are ones named that. And then, older, he wasn't very old at the time, Alan Turing came along and said, but actually there's this class of real numbers that are the computable reals that are generated in this particular way. That's kind of the type of problem that we have right now. All we have, in Turing's time, all they probably had in the world of real numbers was named classes of real numbers. But there turned out to be a natural class of real numbers that were computable reals. So that's the challenge here. What is the natural class of these things, where people say, I mean, Jose was just saying, you can have an infinite collection of possible foliations, many of which have scrambled space-time into some insanity that, for example, no observer like us would ever deal with.
Yeah, but that particular case, in the second half of the 1800s, with Dirichlet and others, with Dirichlet cuts and Cauchy sequences, there were at least two models of these infinite sequences. The real numbers.
Yes. So,
but those are not computable, but they had a way, you could talk about them.
Right. And we have a way we could talk about. I mean, we have a variety of ways we can talk about these foliations and multi-way paths and so on. They're just not very convenient.
Yeah.
Dang, there's got to be a solution here. I mean, and the thing is, what we want is to be able to parameterize ones that observers like us care about, which means they can't be unbelievably complicated and sort of random. they have to have some regularity. And the question is, how do we capture, just like computable numbers and computability captures something which is kind of somehow accessible, how do we capture that in the same type of way? Well, at least we understand the problem. I don't know. Okay, there's just, Richard had another set of comments, and we should unfortunately wrap up here about
the GPU case.
Yes, yes.
Causal dependence analysis. Yeah, actually, it's a nice problem I'd encountered, and I was kind of, looking at how could you incorporate these techniques into a sort of more general system. So, linear recurrences have this data dependence between the inputs and outputs. And so normally you would think that such a problem is not parallelizable. And so these guys came up with this nice trick where, based on the signatures, you can sort of in parallel compute your outputs with errors and then do a quick fix up at the end. So that's the idea of like a different computation strategy, which leads to parallelism, where normally people would throw their hands up and say, it can't be done. And I keep coming back to this example because I think it's nice. And also it's quite practically applicable. Linear recurrences appear all over the place.
Okay, so the claim would be that normally a linear recurrence, if we look at the computation graph for a linear recurrence, it's going to be a grid. Is that right?
It would be quite serial, like a sort of single chain of operations, especially if the signature introduces, like I said, the dependence between a data dependence between your inputs and your outputs, so that you can't sort of in parallel compute your outputs, because you need to know the previous answer essentially.
Where did I get the, wait a minute, what did I do wrong here? Why is this? Let's see, with ABC there, help me out, somebody. What did I do wrong? Oh, yeah, right. Okay, so what you're saying is, and it's sort of reminiscent of, I don't know, fast Fourier transforms or who knows what else. Your basic claim here is that there's a way of reorganizing this computation that does not involve, so the most natural form of this computation would be to say at each step, let's see, what is it? Is it a nest? Help me, somebody. Is this a fold pair list or something? What is the operation that you're doing? The natural operation just with f of whatever here. If we say it's the
recurrence table.
Is that what I want? What am I trying to do? Recurrence table. I guess
mean, if you want equational input.
Yeah, right. I guess that, but so what you're saying is f of n plus 2 equals a times f of n plus 1 plus b times f of n. Actually, I want it to be g of that or something. Maybe I'm just confusing myself here. F of n. And then I want to start with, let's say, f of 5. And then what do I do for the here?
It's part of the, you have to give them in a list, kind of like for dsolve, nDsolve, that kind of thing.
What am I doing? I'm doing with f of 5 equals. But why do I do it? Why do I need to give f of 5 explicitly?
You need to give 2 initial values for this to get going. F of 5, f of 4, maybe. Or yeah, or that.
Okay. And then what do I do here? I just say f or f of n.
Yeah. And then you have to say how many n's. What n from, whatever, 1 to 10 or something. And what's that g doing? Oh.
Well, I was trying to do something there that was general function.
I see. I don't see why. What's f actually? F is black. Is f something?
Oh gosh. Well, anyway, but if I'm understanding what Richard is saying correctly, what he's saying is that there is a potentially
summarize at the end. Yeah, essentially there's a foliation which allows you to get to the answer faster. And if you didn't know this technique, you wouldn't be able to do so.
So I haven't read your paper, but we use a technique which is basically divide and conquer. So it gets you an exponential speed up of running these linear recurrences. Is that what it is?
I think not. I think it's something different here.
No,
Okay.
It's like a kind of mathematical trick or whatever. So it's like by introducing errors into your output, you get to this sort of halfway point faster, and then you do a quick serial pass at the end, which you can compute very easily because it's just the sort of generalized Fibonacci series. So what you end up doing is introducing errors in your output which are computable or like trivially computable based on the signature of your linear recurrence. So it's a nice trick, and it has some sort of like practical utility.
Yeah, that's interesting.
But so I mean, your point is that is a particular case. Right. It's the question being addressed is, if you allowed yourself to, are there computations where there is a faster multi-way result, on some multi-way path? Or for example, in the case of the superscalar processors, are you basically saying, Roger, that a superscalar processor is following multiple paths in the multi-way graph for a while?
No, but it has a backup. It has a way of backing out when it makes a mistake. So the performance.
I thought they were doing multiple actual instruction paths at the same time.
They are, but they're sort of separate. They're different parts of the computation. But let's say you have a loop, and you need to predict whether you're going to exit the loop or not. And what can happen is that you mispredict, and now you need to back out a certain step.
Right.
But the fact is that they're very good at predicting. That's why you get such parallelism now. That they're like super good at predicting compared to 10, 15 years ago.
Right. But you're asking, I mean, in what I thought was the case, and I thought that was the source of some of these horrifying bugs, was that the CPU actually preemptively does multiple evaluation chains. Is that not the case? It's actually executing, saying the result would be this or this if I were to go in this direction.
Yes. And that's what they need to back out of when it becomes clear that it wasn't where it was going.
Right. But I mean, the point of this is that CPUs are doing junior multi-way computation, maybe.
Yeah.
They're doing local multi-way computation. And so then this would be, this is about kind of the bigger calculus.
Yeah, Richard, you're right. That's called speculative. Yeah.
Yes, speculative execution, exactly. Right, and I don't know how many paths of speculative execution they do, but this is the same type of idea, I think.
Not much, because you're gonna lose out very quickly.
Because
they grow so quickly, so you what is that? Okay.
That's interesting. Okay. Multipath. Yeah, well, okay. So anyway, I got to go because I'm super late for some other meeting here. But this is okay, guys. Well, I mean, I think this is very interesting stuff, but it's clear there's a certain amount of heavy lifting, especially given that we're trying to solve a problem that I at least have been thinking about off and on for 40 years. But it is also very interesting to see that this problem is sort of a convergence of same questions that have come up in lots of fields. I'm telling you, there's an analogy between, all these named strategies. I mean, it is a little bit interesting that Turing machines don't have a natural way to generate algebraic numbers, for example. In other words, the branch of the named numbers is separate from the branch of the systematically generated numbers, for what it's worth. Anyway, I mean, okay, last thought maybe from Jose. Is there anything you can imagine, like any constructive method for producing gauge choices, aka foliations in general relativity? Or is it just, write it down?
So there are two different things. One is general coordinates. That's like choosing functions. There are just too many. The second thing is the physically useful coordinate ones, and then the ones that observers would construct. And then there are named very important ones like Fermi coordinates. I think so.
Yeah, right. But I mean, but I mean, right. But that's the point. We're again at named coordinate systems. The question is there a systematic way of constructing a coordinate system like a Turing machine, like an operational calculus of some kind for generating coordinate systems? That's the question. Like, imagine that you were building a network of clocks, actually building it, which effectively amounts to constructing a coordinate system.
But if there is a physical process, then you can define the process, right? And
yeah,
you say, I send light rays and they go and come back. And
I know
this type of thing, right? And
yeah, exactly. But I'm looking for something which is kind of like a Turing machine, as in there's this particular type of, constructor kit that you use to set up your light ray. It's like you've got an optical bench and you've got various kinds of lenses and splitters and this and that and the other that you're using. And what are the natural, primitives that you might use? Anyway, I unfortunately have to go to a different meeting about a very different topic, which I'm really late for. Well, thanks everybody. And we'll try to sort of focus in a bit more carefully on what it is we're trying to move to next. But this is very useful. And thanks until the next time. And thanks to folks on the live stream also.